Okay, we're in the last section of chapter 19, and we're going to talk about the Doppler effect in bow shocks, and uh, we'll see. We've all had this experience. I mean, it doesn't necessarily have to be a siren or a whistle or anything like that. If you've ever been stranded on the side of a highway, you had to pull over to change a tire or something like that, you'll hear the cars passing by you. And as they pass by you, if someone honks a horn while they're passing you, you've certainly heard the Doppler effect. But if you just the cars passing, you'll hear this, there's a change in frequency of the car approaching. The engine has vibration, and as the engine is approaching you, you hear it at a high vibration, and as it passes you, it lowers in vibration. We've all had this experience of the Doppler effect, and they're showing here what you're seeing is as the siren approaches you, uh, you have the speed of sound uh, coming the siren coming at you, but you also have the additional speed of the fire engine coming towards you. So the waves are compressed, and you hear a higher wave than you normally would. And as it passes you, the since the fire truck is moving away from you, the it lowers the frequency of um, the waves that are coming at you. Now the wave speed is the same, but the frequency varies. So this is the Doppler effect. The Doppler. Let me dismiss my image. Oops. The Doppler effect is an increase or decrease in the wave frequency perceived by an observer in motion relative to the wave source. So you could be in a car, hearing a some kind of horn or something like that, and it's if the horn is stationary and you're moving, you'll still get the Doppler effect. Or if you're stationary and the horn is moving, you get the effect. So if the observer moves toward the source or the source moves toward the observer, wave frequency increases. If the observer moves away from the source or the source moves away from the observer, wave frequency decreases. It applies to sound and to light. The astronomers use the Doppler shift if some planet or galaxy or something like that, if it's blue shifted, that means it's coming towards the observer. If it's red shifted, where the red wavelengths are longer, it's moving away. And you can tell rotation. If you're looking at an object and it's rotating, the side that's rotating towards you will be blue shifted, and the side that's uh, spinning away from you is red shifted. So it applies both to sound and to light. You even when I had a Doppler sonogram when I was looking at my heart, and I'm in a position where I can see what the tech is doing, and I asked him. I said, "Is that do those colors indicate the flow of blood?" And he looks at me kind of surprised that I figured out what he was looking at. And yes, it is. The blood was flowing away from the little meter. It was redshifted as the blood was moving towards the uh, the the little sensor. It was the blood coming towards the sensor. So they use Doppler shifts in sonography also. I know I've got lots of students that are sonographers, so that may be of interest to you. Okay, let's continue on. Uh, Doppler effect of light. I already discussed this, but we'll read it on um, the the slide. The blue shift increases light frequency toward the blue end of the visible spectrum. Again, it means it's moving towards you. The red shift is a decrease in light frequency toward the red end of the visible spectrum. Example, a rapidly spinning star shows a red shift on the side rotating away from us and a blue shift on the side rotating toward us. There, there used to be I mean, there probably still is, and maybe I should get one. There's a T-shirt that on the front of the T-shirt, it's got the blue words. It's got Doppler shift in blue, and on the back, it's got Doppler shift in red. Because if you're coming towards someone, it's going to be blue shifted. If you're walking away from someone, it's red shifted. I should get one of those T-shirts. Okay, the Doppler effect occurs in sound, light, both A and B, or neither A and B. Well, we just discussed it's in both A and B. The Doppler effect occurs for both sound and light. Astronomers measure the spin rates of stars by the Doppler effect. Okay, now bow waves. The waves superimposed directly on top of one another, producing a wall. An example, a bug swimming as fast as the wave it creates. There's a little story in the text about a little bug that's moving up and down, creating waves, but as he's moving up and down, he's also moving forward. And if his speed matches the speed of the waves, then you get this effect. You get the bow wave, and then it also happens with supersonic aircraft flying faster than the speed of sound. I grew up in the 50s, and back, we live here, by Lackland and Kelly, and I mean, when I was a kid, those were active air bases, and it was very common to hear a sonic boom. I think now they limit military aircraft over residential over cities to not produce sonic booms, but they were pretty common when I was a kid. So an aircraft that flies faster than the speed of sound will produce a boom. It's compressing the air so much as it goes beyond the speed of sound that it sends this shock wave to the area below it. So a bow wave, the V-shaped form of overlapping waves when an object travels faster than the wave speed. So this is less than the velocity of the wave. This is V equals the velocity of the wave. Here you exceed it, the velocity of the wave. You get this bow shock, and if you greatly exceed it, then you can see it's a narrower angle. An increase in speed will produce a narrow V shape of overlapping waves. Okay, the shock wave, a pattern of overlapping spheres that form a cone from objects traveling faster than the speed of sound. And you can see there's a shock wave at the front of this plane, and you can see the shock wave at the end of the plane. So you actually get like this double shock. Most likely you're not going to hear a sonic boom in this area. Okay, so the shock wave consists of two cones, a high pressure cone generated at the bow of the supersonic aircraft, and a low pressure cone that follows toward or at the tail of the aircraft. It is not required that a moving source be noisy. In other words, it doesn't, I mean, if you got a jet plane, it's going to be noisy, but even if it were not making noise, you would still get the shock, the sonic boom, because it's a pressure wave, not a sound wave coming from the engines of the airplane. Okay, the sonic boom, the sharp cracking sound generated by a supersonic aircraft. The intensity due to overpressure and under pressure of atmospheric pressure between the two cones of the shock wave. So supersonic bullet, the crack of a circus whip. So if you crack a whip, your that crack that you're hearing is actually the tip of the whip moving faster than the speed of sound. And that's the end of chapter 19. Very good.